Okay, so I got some questions about these like coin flipping ones, and what are the chances that different outcomes actually occur. So we want to go through this one, and we'll just how do you approach a question like this? So let's start with the idea that we flip the coin 5 times. So we're going to start with a question like this with defining our sample space. 5 flips. Now, in 5 flips, if we think about it, there are, there's the first option, second option, third option, fourth option, fifth option, right? These are the 5 sort of events that are going to take place. And what we want to do here is use the multiplication rule to count out how many different options it is that we're looking at. So if you think about it, the first flip, there's two options. Second flip, there's 2. The third, there's 2. The fourth, there's 2. The fifth, there's 2. So we have 2 to the 5 possible flips, right? And of these, so 2 to the 5 is 32. So there's 32 events for us to consider in the sample space. So the trick with this is trying to figure out exactly how many we can count here. So for one head coming up, what the options would be there, quickly, there would be head, tail, 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 head, there'd be tail, head, tail, 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 head, tail, there'd be tail, 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 head, tail, and then there'd be tail, 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 head. Okay, those are all the different ways that you could exactly one head could come up, right? Let's just change this quickly so it says exactly because it needs to be particular. Okay, so the chances that one head comes up, well, we know that for flipping a coin, actually this is nice and easy because we know that the probability of heads is 0.5 and the probability of tails, I guess we could also call it head complement, is also 0.5, which is nice, right? Because it means that all of these equations are essentially the same, right? They're all going to be 0.5 to the power of 5 because the probability of something happening and something else happening is multiplication. So the probability that each one of these things happen is 0.5 to the power of 5. So 0.5 to the power of 5 is equal to 0.03, and let's just give it 4 decimals so we can see that. So 0.313 or 0.3125. Now, each one of these outcomes has the same probability, right? The chances that I throw a head on the first throw are just as good as throwing a head on the fourth or fifth throw. So each one of these are actually the same. So we can say there's 5 different ways to do it. Each of these ways has a 0.03125 chance. So we can go probability one head is equal to this number that we found times 5 different ways of doing it. So there's 15% chance to get exactly 1 heads if you throw the coin 5 times. Now, at least 1, right, is a bit different. At least 1 means that maybe we get 1, maybe we get 2, maybe we get 3 or 4 or 5. So we would have to look at these chains and repeat them for 2, 3, 4, and 5. So we'd have to do this 4 more times. Unfortunately for us, there is a bit of a better way to do this. If you watch the at least 1 video, you could see that. But if not, the probability of at least 1 is equal to 1 minus the probability of none, right? Because the chances that you get at least 1, the opposite of at least 1, the complement, is that you get nothing. You get none. So if we start with 1 and subtract the chances that we get none, that gives us the probability of getting at least 1. Now the probability that we draw no, we flip no heads is easy. It's tail, 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 tail. That's the only way to do it, right? And tails, that's only one option out of 32, which is conveniently is actually also equal to our result from before, right? I mean, another way to think about this result is to think about it as 5 over 32, which is equal to, right? I'll just quickly calculate this. 5 divided by 32 is actually the same number, right? Because we did it the sample space way, and we also did it the probability way. So the sample space is 32. There's 5 different ways to get one head. 5 out of 32 is 15.63%. To get no heads is to get all tails is 1 out of 32, which is a considerably lower chance here. I'll just rearrange this so it's fraction. And there's only 1 out of 32 ways that we could get no heads. Therefore, the probability that we get at least 1 would be 1 minus 1 over 32, which we say p of at least 1 is equal to the other 31 ways, 31 out of 32, right? So you can see now that the way we could have done this before is we kept doing it this way, where we counted up all 31 different ways of getting at least one head. But the much easier way is, of course, to just consider the opposite, that there's only one way to not get a head, which is to get 5 tails in a row, and therefore there's 1 out of 32 ways not to do it, so there must be 31 ways to actually do it. Last one here is about exactly four heads. Now, again, there's a lot of different ways that this one could go, but you want to sort of observe something here about the exactly 4 and exactly 1. Look at the exactly 1. How many tails come up in each of these cases, right? 4, 4, 4, 4, and 4. So you see that exactly 4 heads is the same idea as exactly 4 tails, and this is actually going to be directly equal to my answer for A, right? Getting 4 heads is the probability of 4. It's the same probability as 1, because if you just flip what's a head and what's a tail, the probability doesn't change, right? They're both 50%. So equals, 5 out of 32. It's useful when you're working on these ones to realize that the way to distribute these rules always follows the rows of Pascal's triangle. So if we know, for instance, when we have 5 events, the 5th row of Pascal's triangle is 1, 5, 10, 10, 5, 1. And notice that this adds up to 32, right? Which is what I said was the sample space in this case. So the probability of, 0 heads is 1 out of 32, because that's the first row from Pascal's triangle, the first entry. The probability of 1 head is 5 out of 32. That comes from the second term there. The probability of 2 is equal to 10 out of 32. Probability of 3 is also equal to 10 out of 32, because again, 3 heads is the same thing as 2 tails, and we already looked at the probability of 2. Probability of 4, now we just keep repeating, so 5 over 32 again. And the probability of 5, which is, again, think about 5 heads as the same thing as what we did before. It's like 0 tails, right? Which is only one way to do that, 1 out of 32. Now, according to our quick way of doing this, the at least 1, for example, we said it was 1 out of 32 because we did 1 minus the complement. Now I can actually add up all of them. I can start with 0 plus 1 plus 2 plus 3 plus 4, and I can actually check them, right? I don't need to make every single pattern because I know that they have to follow this particular pattern, which we're going to look at, in the future, but we can use it for now to help. 1 plus 5 plus 10 plus 10, so that gives us 26, plus 5 gives us 31. So the probability of 0 or 1 or 2 or 3 or 4 or 5, or sorry, not 5, that's not included, right? Sorry, 5 is included, it's 0 that's not included. Probability of 1 or 2 or 3 or 4 or 5 equals the probability of 1 plus the probability of 2 plus the probability of 5, right? We add them all up. And what we found here was that this is equal to 31 over 32, which is our other way of doing it if we don't use the complement method. So hopefully this has helped with the idea of coin flipping. Coins are nice because both events have a 50% probability, so it's nice and easy to just use this method, right? There's 10 ways to get 2 heads and 3 tails. There's 10 ways to get 2 tails and 3 heads. There's 5 ways to get 1 of each. And there's only 1 way to get none of each. So in this case, we can answer any of these questions by using this method here, this 1, 5, 10, 10, 5, 1. It tells us all the different probabilities that we need.